Hello, my name is Michael Warren, and today I'm going to be going over the coding that my group and I have put together for Project 2, Numerical Analysis. My name is Michael Warren, like I said. My partners were Jerry Tristan and Hinna Calderon. For starters, the first things that we put on our code obviously is clear, CLC, close all, so it gets our housekeeping commands out of the way. Next, we have a couple of comments. So the initiating variables for our menu, data validation, and counter. And then we have our user inputs, which were equation threshold, XL, and XU. This is just a brief explanation of what we will be using in our code, some of the variables that we're going to encounter. So for the beginning of the code, we get our while loop going. Since the problem asked us to put both parts within the same while loop, we began the while loop here, and we'll check that all of the uh, requirements have been met at the end to decide whether or not we're going to repeat, which the requirements in the end become whether or not the user chooses to select to enter any more values to run the code again. So first thing in the while loop is we start with the first problem, which what we're attempting to do is retrieve a matrix from the user, convert that matrix into an upper triangle matrix, and then solve that matrix and give the user back some data. So the first thing we get is user matrix from an input function. We then find the size of that matrix in order to do calculations with it, because we'll need the size to do the calculations. Then we check whether or not the matrix we've received is the proper sized matrix, which needs to be an n by 1, n plus 1 matrix. If the user has met these requirements, we move on and send our variable to the functions. So the first function we have here is uptree, which if we pull it up is the function that goes ahead and puts that matrix that we received from the user and converts it into an upper triangular matrix. So we first receive the matrix, we find the size, and then we go through converting each row into a vector which begins with a 1. So we actually go to a reduced form of an upper triangular matrix, which actually makes it slightly easier to solve for each of the missing values. Once we have done this, we check whether or not the solution to the matrix, or I guess we check whether or not the matrix has more than one solution. This is going to be our tick. So we begin by checking whether or not the bottom row of our matrix is full of zeros. If it is the case, then we know this matrix has more than one solution, and we stop the coding and we let the user know that the matrix they entered did have more than one solution, and thus we're not able to return specific values for them. If that is not the case, from that point we move on to our second function, which is named backsub, and that is going to solve for the missing values. So if we pull up backsub, we start by retrieving our matrix and finding the size right away so that we can use our for loops, etc., to calculate what we need. The first thing I do is we set up a variable vector so that we can store the values that we're searching for. And then we go down to the next part where we are going to display our matrix, our original upper triangular matrix, before we make any changes to it. This way the user can see what their matrix was turned into before they actually got their solutions. This here just renames the matrix and displays it for the user. After that, we go into calculating the solutions to the matrix. We start by going through and applying the first, so we take our upper triangular matrix and we take the solutions column, which is the final column, and basically we divide out each value to find the variable. So with an upper triangle, the bottom row only has one variable so we're able to take the solution value, divide by the 1 coefficient, and get our variable, which is what we do here. The first thing we check is whether or not our count is greater than or equal to 0, is greater than 0, which it's not in the first case, and so we skip on and we do like I said, which is where we calculate the bottom row value. Once we've calculated the bottom row value, it stores it in the first part of variables, and we go to the top. Now count has been increased by 1, and we're going to run through this if statement, which calculates our minus value. Now the minus value is going to be used to find the other variables located in the higher up rows. When we move on to the second row, there's still only one variable, but only because we have the variable from the first row. So we need to account for that variable. We need to multiply it by the coefficient and subtract it from the solution column in order to find our new variable, which is what our minus is. So our minus becomes the new variable multiplied by the coefficient being this value here, the new variable being our first part of the variable's vector. Once we find our minus, we move on down to here, which is then no longer a 0, and thus it is accounted for in calculating the second and the third and so on, depending on the size of the matrix. Each one of those additional values or variables which the user needs to find in order to solve the system of equations. After that, we rename that value as solved, and we send it back up the function train, so it goes to the top of this. It's sent to uptree. Uptree then sends it back as well, along with the upper triangular matrix and solutions vector, which contains the variables which we solved for. And then our original main script takes all of those values, and it goes ahead and produces fprint statements to display them to the user. This is the initial part of our problem, which we can run here for you. If we go up and enter our matrix, the first thing that you notice that it'll give is the upper triangle matrix. It is reduced, so each value at the beginning is 1, and the bottom half of the triangle is zeros. This last column here is the solutions column, as I mentioned before, which is used in the calculations to solve for the missing variables. We then display the solution matrix to the user as well, which gives them their x1, x2, x3, and so on, depending on the size of their matrix. Now I'm going to cancel this here before going on into part 2. So now I can go through here and I can explain the second part of the problem. So for problem 2 of numerical analysis, the first thing that we do is receive an equation from our user. Basically what we're doing in this part is we are using the bisection method to determine the maximum amount of error that exists when approximating the root or roots of a polynomial. So the first thing that we need to receive, obviously, from our user is the polynomial itself, which is stored in an equation. We then make sure that equation is the proper size. So if the vector that the user gives us is not proper size here, it will then ask them to please re-enter the value again. And if we do not receive the value again after 2 tries, then we stop the program, and the user then has the option to look over their data again to double check that they have what they need, and then to try again. However, if they did enter their correct size matrix or vector, we then move on to the next part of our code, which then asks them for the maximum acceptable error. Now, this is going to narrow down our calculations to within this range here. So they enter their threshold. We make sure that the threshold is a positive value. Otherwise, a negative threshold doesn't. No calculations will be within those bounds. So we get our maximum threshold, and then we get our bounds of the function itself. Now, to calculate any roots, a function has to cross the x-axis. So when entering these bounds, the user needs to pick a point left of that cross and right of that cross. In other words, one of the values should be a negative y value, and one of them should be a positive y value. So when the user enters these, we then double check that that is in fact the case. So we check the sign of xl and the sign of xu, and if the user has indeed entered those values correctly, we then send our values to our functions. So the first thing that we need to send is our vector that they gave us, the maximum error, the lower bound, and the upper bound to our function bisect root. Now, if I pull up bisect root, what we do here is we receive the equation, the threshold, and our lower and upper bounds from the user, and we go on to calculate the roots and the number of iterations using these variables. So first we rename them, we go on to find the roots with the bisection method, and then we approximate the root after each iteration, and that is saved into our max error points at n, which we will go on to calculate the error from those to the actual root. So once we have that, we take our root approximation as xm, the final value after all of the iterations. We calculate, we store our number of iterations in num iterations, and our maximum error is equal to the absolute value of our final x2 minus our final x1. After we have those numbers, we display them to the user, and that just about sums up the calculation part of our coding. The last thing that we have to take a look at here is bisect root 2, which is our function designed to graph each part of what the user is going to see. So this is the function which will use our polyfit. It's going to take all of our data points, find a line of best fit, then it's going to graph our number of iterations on the x-axis, and it's going to graph our values of the root approximation on the y-axis. After that, we plot the best fit line and the data points, and we label our graph, etc., etc. We take our detailed points basically at that. We move on to our root approximation in between each iteration. We find the absolute values for the root vectors. And then for our data validation, basically we're making sure that the values that we have work properly with our the graphs that we're intending to make. Once we make sure that these values are all correct, then we are able to take the x values between each iteration, the y value function at each iteration, and we're able to plot those in order to give the user a visual representation of the process. So the value that we got at first iteration compared to the second iteration compared to the third, all the way down until we got our approximation that was as close to the root as possible. And then lastly, we labeled our graph to make sure that all the labels were easily understandable to the user. And so overall, that is the coding that we have prepared for our project. And really the last thing that I wanted to talk about with this code is just the limitations of it, as well as some of the uses that it could be used for in engineering, just in the engineering field. Really, numerical analysis is a humongous part of engineering. Obviously, there's a lot of numbers involved, all of the maths, the statics, the dynamics, the etc. The classes that engineering students take all revolve around these mathematics and numbers, and obviously, as a result, analyzing those values and actually seeing how the approximations and how your average error and your maximum error and those things, how they all play a role in creating buildings and pipelines and all of the things engineers do, based all on these numbers that need to be within certain ranges. And to some extent, that's something that this program, or a type of program like this, could do. Obviously, the limitations with this is that it's fairly specific to a system of linear equations, and it can't necessarily calculate all of the limitations for the maximum pressure in a pipeline, etc. So the limits of this are to mostly analyze a graph and values that can be put into a graph and viewed from that angle. So really, this is it's a very interesting code and process, and going through this all has really taught us a lot about
what engineers need to do and what they need to analyze and how they need to view things in order to properly do their jobs. And so that's really it. That's what we have for our project. I hope you've found this video to be interesting and informational. And thank you for listening. And I hope you have a good day. Thank you.